Okay, so last time we started a new topic on oscillations. So an oscillation, they're very common in real life, right? We do see oscillations all the time, and then waves, right? And then you can make an oscillator. The simplest one is just use the spring, attach something to a spring, and pull it to one location, let it go, it's going to oscillate back and forth. Or another oscillator you can make is a pendulum, right? You make a pendulum, pull it to one side, let it go, oscillates back and forth, okay? So, and then we define period, because when it's oscillating, goes back and forth. So we define period of the time for one full cycle. So it starts from the initial point, goes to the other side, comes back to the original position. That's the period. And then another thing we define is the frequency, 1 over period, right? So this guy, the unit is 1 over second, but we call it hertz. And then another thing we define is amplitude. Amplitude is the furthest displacement from the equilibrium position. So that's obvious. So that's the we usually use these parameters to describe an oscillation. Okay, and then we started with the simplest oscillator. That's called a harmonic oscillator. A harmonic oscillator is an oscillator where the force, the restoring force, to pull it back to the equilibrium is always proportional to the displacement. And this symbol means proportional to. And then we have learned that Hooke's law for spring, right? Hooke's law is like that, right? The force in the spring is going to be negative k delta x, right? So anything obeys Hooke's law when it's oscillating, it's a harmonic oscillator, okay? So that's what we want to study. Now let's make a simple harmonic oscillator, an ideal oscillator, where you just attach something to a spring in horizontal frictionless surface, okay? Like in slide 4, lecture 20. So you attach, this is a spring, you attach something on this, to the spring, and then on a frictionless surface, the friction is almost zero. And in this case, you pull it to this side, right? The spring is going to want to pull it back. You let it go, it's going to oscillate back and forth. If there's no friction, it's not going to stop, right? So that's a harmonic oscillator. And then the force is always going to be like that, right? That's, the restoring force is always proportional to the displacement, but in the opposite direction, okay? Now we can, what we can do is this. We can actually solve that equation. Why? Because we know that this force, the net force on this object is going to be equal to mass times acceleration, and in x direction, right? And the only force, no, there are 3 forces on this object: gravity, normal force, and then the pulling force from the spring, either in that direction or this direction, but doesn't matter. This is the only force on this object. If you pull it and then you let it go under the force from the spring. Then if you connect them, so the net force on this left-hand side is just going to be negative kx, and this is max. Now I'm going to make use of the definition of the acceleration. The definition of acceleration is this. Now I'm going to do derivative, okay? Acceleration equals dv over dt, right? Now I'm changing the delta to d, different. And then v is dx over dt, right? Because v equals changing distance divided by changing time. Now this is just the second derivative of the distance over with respect to time, okay? All right. So now you substitute into this equation. You get negative x, kx equals m, then this. Okay, you can actually solve this equation. You can solve this equation. This is just going to be a differential equation. You rearrange it a little bit, you will get this, right? So d squared x. Now I'm going to put this thing to the left equals negative kx. So it's going to be this, k m and then times x. Right? If you rearrange that, you will get that. You can solve this. We're not going to solve it. We're just going to go ahead and use the conclusion. The conclusion is this. You solve this, you will get a very precise solution. Okay? That's why we want to always start with the simplest case. It's going to be equal to a constant a, cosine function, and then this times t plus a phi angle, which is an arbitrary angle. Okay, this is going to be the general conclusion to this differential equation. This is a conclusion, right? You do the math, you will get this equation. And don't forget what this x is. This x is just the position of this oscillator. So basically, we found the function for the position of this oscillator. Because when it's oscillating, the x changes, right? The x definitely changes, okay? But if you solve it, right? If you solve it, you will get a function of the x at any time. So that means once I have this complete equation, if I have all these numbers I need, I plug in a time, I can always predict the position of this oscillator, right? Because it's oscillating. What's the position of this guy at 5 seconds? Maybe here. What is the position of this guy at 10 seconds? Maybe here, okay? But if you use that equation, you can make that precise prediction. Give me all these numbers. I'm going to plug in 5 seconds, 10 seconds. I will always give you the position of this oscillator, okay? So that's the conclusion we want to use in this class. So for any simple harmonic oscillator, this is going to be the conclusion. So that's the equation we derived in slide 5. Now, usually what we do is that I don't like writing this thing. I don't like this, okay? So I'm going to define it, right? If I don't like something, I just define a new name for it, right? I use a new symbol for that. So I'm going to call this angular frequency. So this is just the angular velocity we learned earlier, okay? But in this case, it's related to the frequency, so we'll always also call it angular frequency, okay? Now, then this is much nicer, right? This form, and then I'm just going to tell you, how do you find this omega? In this case, you do this, okay? Because that's the original solution. I wanted to write it in a nicer form with one symbol here, so I'm just going to define this symbol to be this value. So this is called angular frequency or angular velocity we learned before, right? This is still omega. This A is amplitude, because you can see that what is the maximum value you can get from cosine? 1, right? So this guy is always going to vary between 1 and negative 1, 1 and negative 1. So the maximum value this x can get is going to be A or negative A. But that just means, negative sign just means it's going to be either on this side at the maximum A, or on that side with the displacement A, right? So, and then this phi is the phase constant. So it totally depends on where you start counting, right? You let it go and then you have a stopwatch, like when do you want to count? You can pick any time you want. But if you always pick the time 0 at the maximum displacement, like I pull it here, I let it go and then I start the stopwatch at the same time, then the phi is going to be 0, okay? Of course, if you let it go and then you pull it, let it go, and then when it passes the center, past the equilibrium, you start the stopwatch, you will get 90 degrees. So this phi angle totally depends on how do you count the time, right? So in this class, we're just going to always do the t equals 0 at maximum displacement. So the phi is always going to be 0 in this class. We don't need to worry about it, because this is a totally arbitrary factor. We don't want to worry about that. Okay? And you take a look at the graph on slide 6. That's the graph of the x versus time, right? Because this guy, remember the x is the position of this object. So the position gets larger and smaller, and then large on the other side, and then smaller on the other side. So positive, negative, right? If you make a graph of the x, so x positive, larger and larger, and then reaches this side, reaches the maximum here. Now go back to 0, now back to here. Now it's not going to stop here. It's going to go to the other side, increase, reaches the maximum on the other side. That's why we call it negative. And then go back to equilibrium and just going to continue. Right? So this is the maximum A. This is the maximum negative A on the other side. So this is going to be the graph, xt graph, the position time graph for this oscillator. So it's going to be a cosine. You see that it's a wave function, sine or cosine. But if we say that we started from here, we call it cosine, okay? So if I start my origin here, I start my, right? If you start the origin there, that's a sine function. If you started from here, that's cosine. So that's what I said. The time where you set a 0, it's going to determine this phi, this initial angle. But this is what we're going to do in this class. I'm going to start counting when I pull it at this point, so maximum displacement, and let it go. That's my 0 point. Okay, so that's going to be maximum. So that's when phi equals 0. Okay, so in this class, phi is always 0. We don't need to worry about it. So this is the complete equation, complete solution to that. And then we can also find the period using this omega. Because remember, how is omega connected to period? Omega is changing angle divided by changing time. Remember that? And then if I pick a period at a time, I will pick the angle it rotates in one period, that's 2 pi, right? That's what we're doing in rotations. Then you see that, oh, now I can equal this to this. So I will get equals 2 pi over a period. And then I can find the expression for period. You rearrange this equation, that's what you're going to get, okay? So this, again, this is not a new theory. This and this, they're going to be given, okay? And then once you have this, the idea in this part is this. Once you have this, then you will be able to figure out everything in this part. This, you just make use of the definition of omega, the angular speed or angular frequency, okay? And then, frequency, well, you just take inverse of this guy, you will get the frequency, okay? So I'm not going to write it, because they are just inverse. The frequency is just inverse and the period. But you can see the period doesn't depend on the amplitude. It only depends on the mass and the K, which is the spring constant. So this may not be very intuitive to people, because you see that means if I'm going to make an oscillator using the spring, I pull this mass to this location, let it go. It's going to go back and forth, back and forth. I can measure period, say t equals 5 seconds. For 5 seconds, it's going to complete. Goes to the other side, comes back, 5 seconds. Goes to the other side, 5 seconds. If I just pull it a little bit shorter, I let it go. It's going to go to the other side, shorter, comes back. It's also going to complete the cycle in 5 seconds. That may not be intuitive to people, but this is the theory, right? You see that once the mass and the K don't change, I'm still using the same spring, I'm still using the same K, then the period is always going to be the same. It's not going to change. So it doesn't matter how far you pull it away from the equilibrium. You let it go, it's always going to complete the one cycle in the same period of time. Well, I can sort of explain that intuitively, because think about this. If I pull it a little bit farther, then okay, for one complete cycle, it's going to travel more distance, but it's also going to get a larger speed, right? Because when I pull it to very far away, the force in the spring is going to be larger, So the acceleration is going to be larger. So when it's moving, the average speed is going to be larger. So if you put it at larger in amplitude, you let it go, on average, it's going to move faster. So that's why at the end, the period doesn't depend on the amplitude, doesn't depend on how far you pull it. But again, you should be careful. Don't trust your intuition. Always trust math, okay? Your intuition is not always going to lead you to the right answer. Math is more reliable, okay? Now, once I have this, I can also derive the expression for velocity and acceleration, okay? All I need to do is just make use of the definition of velocity and definition of acceleration like we did, right? To solve this, to get this expression, because velocity in x direction is just dx over dt. You take the derivative, what do you get? You just get this, right? A doesn't change. You take derivative of cosine, you get sine, negative sine. You get negative sine. No, what am I doing? You get a, and then negative sine this function. You're going to use chain rule. You're going to take derivative of omega t, you get an omega. So at the end, you will get this. Negative omega a sine omega t plus phi. You see that? Everything can be derived from this too. Everything can be derived. Now you can do acceleration, because acceleration equals dvx over dt. You just take derivative of this guy, you get omega a negative. You take derivative of sine, you get cosine. And then you're going to take derivative of omega t, so you're going to get another omega. So at the end, you will get ax equals negative omega squared a cosine omega t plus phi. Okay, you see, everything can be derived from this. That's what we're learning in this part, okay? If I'm given this, I can derive t, I can derive va, okay? That's what we're learning in this part. And then, of course, you can call this thing maximum velocity. What is the maximum velocity? That's going to be omega times a. Once you derive this, right, because this sine function is going to only vary from negative 1 to 1. The cosine is also going to vary from negative to 1. Then what is the maximum velocity you could get? That's going to be omega times a. What is the maximum acceleration you can get? That's going to be omega squared a. Again, these are not conclusions I need to remember, right? Otherwise, it's going to be too many conclusions I need to remember. And then you can make use of the omega definition, right? You can write these two guys, okay? So these are some definitions we can derive from this theory, right? Now, let's see. Now let's practice this. Let's practice this, okay? So let's take a look at the question on and then you can also see the graph of this velocity and acceleration on slide 8, right? They're also wave-like, because they're also sine, cosine, right? All right, now let's take a look at the question on slide 9. Again, you're going to put your calculator in radians, okay? Everything is in radians in this part, okay? Because this is going to be in radians per second. This is the angular velocity or angular speed. No, angular frequency, I'm sorry. All right? So 200 block is connected, okay, so it's this, right? It's connected to a light spring with a spring constant. The K is given. The block is displaced 5 centimeters from equilibrium and released from rest at t equals 0. We want to find the position of the block when t equals 3 seconds. If I want position, that's the position function. This is going to be given on the test. So all I need to do is plug numbers in. Do I have all the numbers I need? Amplitude, that's 5 centimeters, right? So I do have the amplitude in this problem. Now, what is this omega? Well, it doesn't give you omega, but omega, that's definition, right? This definition will also be given, right? You don't need to remember definition. So it's going to be this. And once you have that in the phi, as I said, in this class, you never need to worry about phi. Because we're just only going to start the time when it's at the maximum. So we pull it at maximum, then start time. So that's going to make this phi 0. All right, so, okay, so all you need to do is just find the plug it the time in, 3 seconds. You can find the displacement of this position, this oscillator. All right, pause the video, try this with your calculator. All right, so the omega, you plug all these numbers in. The K, what is K from the problem? 150 newtons per meter. The mass is 0.2 kilograms. All right, plug all the numbers in. The omega you find should be this radians per second. Okay. Now I can plug numbers into this equation, right? Phi equals 0. So x at 3 seconds. It's going to be A times cosine omega t. You plug time 3 seconds. Make sure you put your calculator in radian mode in this part, okay? So you will get 0.044 meters. Okay? So this is the displacement. Now, the next part, slide 10, I want you to find the speed of this guy at 3 seconds. Okay, speed. First of all, you need to know how to take derivative. Right? You have already taken calculus. You know how to take derivative. Right? Once you take the derivative, you will get this expression. Right? Again, phi is going to be 0. Do we know omega? Yes. Do we know A? Yes. Time, plugging 3 seconds. Okay, you see? I already have everything. Once I derive this, plug numbers in, you will get the speed. All right, so I hope everyone has already done. So the number I got is negative 0.63 meters per second. I get a negative velocity. Did I do anything wrong? No. Take a look at the graph on slide 8. The velocity is also oscillating, right? When it's moving, right? Oh, I already erased that. When it's oscillating, right? It's going to oscillate this way and that way, this way and that way. Of course, the velocity changes direction. How do we take into account that? How do we distinguish the velocity this way and that way? We call one positive, one negative. Right? So in this case, we're going to call, I believe we're going to call this positive, this is negative, okay? So at 3 seconds, it's moving that way. That's what this negative sign means, okay? You didn't do anything wrong. Don't be afraid of negative sign. They have meanings. Okay? Now, what is the next? Now, next, find the acceleration of the block. Okay? Find the acceleration of the block. First of all, take the derivative of this function, you will get this. That's what you need to know. And then, again, just plug numbers in. Right? So the acceleration at 3 seconds, negative omega square A cosine omega t. In this class, we don't need to worry about the phi because we're always going to make the phi 0. You plug all the numbers in, you should get negative. Right. Again, why is this acceleration negative? Did I do anything wrong? Because it's going to be moving this way and that way, this way and that way, right? The acceleration is also oscillating like this. We call this direction positive, so that direction is negative. Okay? You didn't do anything wrong. The signs are telling you the direction. Okay? So that's this. Now, let's see. So now we want to take a look at, so you see this part, okay? It's mostly just plug-ins, okay? You know this, then you derive the V and A, you just plug numbers in, okay? Nothing fancy, okay? You will also get some problems on the test. Oh no, not on the test, on the homework to practice. Now we want to take a look at the energy. We want to take a look at the energy. The kinetic energy of simple house 12, slide 12. Let's calculate the kinetic energy of this and potential energy of this harmonic oscillator. Okay. Now, okay, I'm going to write this. I don't need the acceleration. No, I don't need the acceleration. But I will still need the velocity. So if I want to find the kinetic energy, well, of course, kinetic energy is also going to be a function of time, right? Because kinetic energy, I still do 1/2 mv squared. Just use this, right? So you will get 1/2 m squared, this whole thing, you will get omega squared, a squared, sine function squared, omega t. No, let's do that because this can be confusing to a lot of people. Sine omega t plus phi squared. Okay? If you want me to calculate kinetic energy, again, I would ask you time. At what time do you want me to calculate the kinetic energy? Because it's also a function of time. Now, elastic potential, because the spring has elastic potential energy, right? So it's going to be also function time. That's going to be 1/2 kx squared, right? That's the displacement, right? So I'm just going to be 1/2 k times that. So that's going to be a squared cosine function squared, okay? And then if you add them together, it's very interesting. So if you add them together, so remember omega k and m, they're related, right? So if I square this, omega squared equals k over m. And then multiply both sides by m, what do you get? You get m omega squared equals k. So that means this is going to be equal to 1/2 m omega squared a squared, and then this cosine squared. Now you add them. You see that the same factor times the sine angle squared, the same factor times the cosine angle squared, and the angle is the same. Well, okay, they are changing, but at any time, the angle is the same. And if you do sine squared plus cosine squared, the same angle, what do you get? 1, right? So that means if I do total energy for the oscillator, even though this k and this u, they are changing all the time, but the total energy, I will get 1/2 m omega squared a squared, right? And then this is going to be k, so I would just do 1/2 k a squared, okay? So the total energy is going to be constant, of course, because there's no work from the outside, there's no friction. The total energy of the system is not changed, right? Because changing energy equals work from the outside. Nothing is doing work from the outside. You consider the spring and the oscillator as one system. You always get a constant because the energy is zero. You see, everything is consistent in physics. Everything, okay? Now, and then does this make sense? Because this is just going to be the energy at the maximum, because this is 1/2 ka squared. So that's just going to be the elastic potential energy when this guy is stretched to the maximum location. And then you let it go. And that makes sense, right? What is the potential energy at this point? 1/2 ka squared. What is the kinetic energy at this point? 0, right? You let it go at this point. Of course, the total energy is going to be 1/2 ka squared. Everything is consistent, right? Even intuitively, you can find by using a simple point. I just use the maximum displacement point. I calculate total energy. I will still get 1/2 ka squared. So it's always like that, right? So if you let it go, you make a plot with kinetic energy and elastic potential energy on the same graph. You will get the graph on slide 12. So the u and k, they're changing. okay? They're changing, but the total is always the same. Always the same because the energy is conserved, okay? Isn't that beautiful? Okay, all right? So this helps us, okay? Again, I'm not going to remember this. I'm not going to remember that, right? Because that's just conclude. If you want me to find the kinetic energy, I would just do this. If you want me to find the potential, I would just do this, right? It takes like a few minutes to do that. And if you want me to find the total energy, this I have a shortcut to remember that. Because the total energy is going to be the same everywhere. So all I need to do, pick this point and find the total energy. What is the total energy? 1/2 k squared plus kinetic energy 0. Equal that. So that's going to be the total energy at any point because energy is conserved all the time, right? So that's how I remember that. Once you understand the theory, it's going to be easier for you to remember that. And this can help us to connect the velocity and the displacement sometimes, which can make our calculations a little bit easier in some problems. Now let's take a look at this question on slide 13. Okay. A 200 block is connected to a light spring, so which is pretty much like this, right? Okay, the same oscillator. The block is displaced 5 centimeters from the equilibrium, released from rest. So the problem is pretty much telling us the A is still, the same. It's the same. 200 block. Oh yeah. Okay, I used the same block. So the A is this, and then the K and the M is still this. So the omega is still going to be, what is the omega? 27.39. Okay, so let's see what we want to find. Find the speed of the block when it's 1 centimeter from its equilibrium position. Okay, if I want to find that, I would just do the velocity. So I would just plug numbers into this velocity equation, right? But you need to know how to derive that. But once you have that, just take derivative of that. Omega, I have that. A, I have it from the problem. Oh, but I don't have the time, right? It doesn't tell me explicitly when this happens. It just says, I want to find the speed of the block when it's 1 centimeter from its equilibrium position. Okay, how do I find the time? There's one way you can find the time. Because I want the time when this position is 1 centimeter from the equilibrium position. So this is going to be 1. So I can use this equation, do a cosine inverse to find the time, right? And then plug the time into the velocity equation. So I'm just using this theory and this, right? But an easy way is to use the energy method. Because we just learned that the total energy of the oscillator is always going to be 1/2 Ka squared. Now if you tell me a point, okay, the total energy, it's always going to be 1/2 mv. So it's always going to be kinetic energy plus elastic energy. It's always going to be 1/2 mv squared plus 1/2 kx squared. That's a general conclusion for any point. But I know that the total energy is always going to be this. Because again, I don't need to remember this. Pick this point, the maximum displacement point. You will get 1/2 Ka squared plus 0 kinetic energy. And that's going to be the total energy at any point, right? So that means, okay, there are easy way to find the speed. Because I want to find the speed when the x is 1 centimeter. I already know the total energy is this. So what I can do is this. The total energy when it's at 1 centimeter, it's going to be this. But I know this total energy is going to be equal to 1/2 Ka squared always, because this is the total energy in this whole process. Then you rearrange this equation, you can find V, right? Instead of using these two functions, so that's easier, okay? So, again, use your calculator, do this for me. All right, so if you have done that correctly, the velocity we found, it's gonna be, what is the number? 1.3 meters per second squared. Okay? All right, so that's the energy consideration in this question. Now, the next oscillator I want to discuss with you is the pendulum. Okay, so the pendulum, it's actually very simple. Okay, so take a look at the slide 14. In this case, we're gonna use the angle as the displacement. Okay, because when you pull it, the angle changes. So we're not going to use the distance because it's a circle. We just use the angle. So the angle is a function of the time. You do this, and then you will get. You do some math, but we're not going to do that in this class. We're just going to use the conclusion. So the conclusion is going to be this. The angle of the pendulum is also a function of time, and it's going to be similar to that. It's going to be the amplitude, which is the maximum angle you pull it, times cosine omega t plus phi. Right, the same, because they are both oscillators, right? So you think, you see, if you use the same theory, a pendulum is the same as the oscillator we just saw. And then omega, again, now omega in this case is going to be equal to this. Okay, so that's a theory for the pendulum. Okay, exactly the same form as that. Now the omega, again, you can derive that. We're not going to derive that. So it's going to be, this little g is just a free fall acceleration. This is the length of the pendulum. Okay, and then again, if you make use of, so this is the theory, you will get this theory. If you make the use of this, the relation between the period and angular velocity, you can derive this. T is going to be equal to 2 pi square root L over G. And of course, you can take the inverse to get frequency. Again, the period depends only on the length. Doesn't depend how far away you pull this pendulum. So that's also very interesting. Well, that's only when the amplitude is very small. If you put it really far away, this is not going to be true. Okay? So this is only true when you pull the pendulum to a very small angle. Okay? All right? This is actually a very useful conclusion because the period of a pendulum doesn't really depend on the amplitude as long as the angle is small. So what you can do is this. You can and then the only thing you need is to measure the length, right? So the period depends only on the length. 2 pi is a constant, little g is a constant, right? So now what I want you to do is this. And then that's very good that theory can be used to make a clock, okay? So take a look at the question on slide 15. Slide 15. On this slide, the question is this. If I want to make a clock using a pendulum, then I just want this period to be exactly 1 second when the pendulum completes a cycle. Okay, you should make the length with what value? Well, in that case, I'm just going to rearrange this equation, right? Because you're telling me that you want the period to be 1 second. 1 second. You rearrange this equation, you can find L. Again, pause the video, do this. All right. So you should find L equals this. So this is about 25 centimeters. 25 centimeters is not very long, right? So it's like 25, this is a meter stick, right? So it's like that. This is about 25 centimeters. So this is a reasonable length. If you you make a pendulum with this length, then the oscillation, the period is always 1 second. So you can use that to make a clock, right? So this is the idea this is a mechanism for the first generation of clocks, okay? If you have seen the grandfather clocks, they always have a big pendulum swing back and forth. That's how it keeps time, okay? And it's very accurate actually, okay? Before the electronic clock comes around, okay? So, and then it was invented in 1656, okay? And then until the 30s, this is still the most precise timekeeper. Isn't it amazing, right? Only because of this very simple conclusion from the oscillator, okay? People can use pendulum to make a clock, okay? Now, of course, now we always use an electronic clock, right? We always use the electronic clock. The idea is the same. It's because quartz, it's a very good harmonic oscillator. So the decay is really low. So the quartz has a very precise frequency and period. Okay, it doesn't decay. So that's why it's very good to use for a clock, a watch. Okay, we're still using the period of this quartz. Okay, it's very accurate, doesn't decay. Okay, it's better than a pendulum. So that's why in modern clocks and watches, quartz is widely used. Okay. Now let's take a look at the last question, 18. Okay. You can also use this to actually determine the free fall acceleration in a different planet, okay? So if you go to a different planet, you want to measure the free fall acceleration, what is the easiest way to do that? Well, one way to do that is just you do a free fall experiment, right? You drop something, you measure the length and time, you can use kinematic equation to find the free fall acceleration. Another easy way is this, you make a pendulum. You measure the length, and then you also measure the period of this pendulum, and you use this theory again to find the acceleration, local acceleration. So let's take a look at the question on slide 18, okay? So on this slide, let's see. You bring a 0.4 meter long pendulum to a planet, and then you do an experiment. You find that it completes 5 full cycles in 9 seconds. What is the free fall acceleration on the planet? Well, I'm just going to use that conclusion we just drew. This is always true for any pendulum, right? And then if the problem says it completes 5 full cycles in 9 seconds, what is the period? 9 seconds in 5 cycles. That is the period, right? And then you plug it in, you can rearrange this equation, you can find little g, okay? Again, pause the video, do it, okay? See if you can find the right answer. Now let's rearrange this equation. Again, I don't like square root, so I would square both sides to get this. First, I don't like denominators. I would multiply both sides by the denominator. Okay, and then you see, how do I find little g? All right, so and then all you need to do is just plug in the length, which is given. This is period, and you can find the free fall acceleration on that planet, 4.87 meters per second square. So that's another way to determine the free fall acceleration on the planet. Okay? All right. So this is going to be the end of the class. Okay? So that's everything I wanted to tell you. I don't know. At this point, I'm recording this video, but I don't know if you're going to watch the video for the last lecture, or I'm going to see you again in this class to finish in the room to finish the class. But anyway, I want to end this class with a quote from a genius we lost 2 years ago, Stephen Hawking. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious, and however difficult life may seem, like right now, okay, there's always something you can do and succeed at. It matters that you don't just give up. Okay, thank you, and then wish everyone a very successful future. I hope to see you soon. Okay, this is the end.